Okay, so now we're going to go through a series of examples, and the whole point of these examples is to show you alternate techniques. Okay, so when you see this problem, your instinct might be, oh hey, I got to use the multiplication property of radicals, and I got to multiply 6 times 12, and then I have to simplify that square root. Okay, well for me, that's a little too much work. I'm going to try a different approach here, which you can apply to if it's just multiplication that you're dealing with and there's no like additions or anything. All right, so I recognize square root of 6 is just square root of 6, whatever. Nah. Now the square root of 12, aha, I know that 12 is 6 times 2. So I can split up the square root of 12 as the square root of 6 times the square root of 2. And I also know, oh hey, if I multiply the square root of 6 times the square root of 6, I just get 6. And that 6 root 2 is therefore the simplified version of that expression. So you don't have to go on autopilot and multiply the 2 by the property and then simplify the radical. That's a lot more work. Sometimes splitting the radicals up like this actually makes your life a little bit easier. All right, so let's continue on with alternate techniques. Okay, now this question here, there's a lot of stuff you can do here. You can be like, oh hey, you know what? I'm going to deal with what's inside the parentheses first by order of operations. And I know the square root of 8 is not simplified. It is really the two square roots of 2. So you can simplify that radical and then cube it and then work from there. Okay? Or you can expand this out and say root 8 times root 8 times root 8. That is exactly what it means. And so, oh hey, root 8 times root 8, that's just 8. And so then I have 8 root 8. And you think you're done. Not really, because root 8 is one of the big 3 that show up all of the time. And root 8, when you simplify it, it's the same thing as 4 times 2, or 2 root 2, right? And so then I'm going to replace this root 8 with 2 root 2. So I have 8 times 2 root 2. And so remember, there's multiplication there. It's implied. I didn't write it there, but it's there. And 8 times 2 is 16 square roots of 2. So that's how I can simplify this one. Now, this next example is an example of my favorite technique. And this is how doing this technique in reverse is how I build the really gross problems in your practice set. But I can chunk this, right? Because if I look at this, oh no, 49m cubed, what am I going to do? Well, I can remember that this is just the square root of 49. That's one chunk. And this is also the square root of m cubed. That's a second chunk. So I'm going to deal with these as separate little problems. Square root of 49, oh, that's easy, that's 7. And the square root of m cubed, well, that's m squared times m. And so when I square root that, I'm going to end up with an m root m. Okay, so I can make this problem more complicated by adding more terms on, but just take it one little chunk at a time. And so now, just for fun, we're going to look at when things are not square rooted. We don't encounter this very often in Algebra 1, but it does occasionally show up, and you do have to deal with it. So what's different here is that I'm looking for the cube root of 16, which means I am not looking for perfect square factors, y'all. I am looking for cubes. And this is the time when that factor tree method actually is very helpful. So I'm going to start with 16, and I know 16 is divisible by 2. I'm left with an 8. I know 8 is divisible by 2. I'm left with a 4. And I know 4 is divisible by 2, and that's a 2 times a 2. Right, so now what I'm looking for, though, I'm not looking for perfect square factors. That is cube root, so I need perfect cubic factors. And I have them right there. So this cube root of 16 is exactly the same thing as a cube root of 2 cubed and a 2 left over. Okay, and so then I can use my multiplication property of radicals. I have the cube root of 2 cubed times the cube root of 2, and cube roots and cubes undo each other, so I'm left with 2 cube roots of 2. So this index tells you how many you need to have together, how many factors you need to have. So if I look at this example here, y to the 7th, I'm looking for y to the 4th power to be able to come out of the radical. And so I can rewrite y to the 7th as y to the 4th times y cubed. Remember the exponent property, add the exponent if I'm multiplying together. Do it in reverse, and then I get the 4th root of all of that, and I can use my multiplication property and split this up into the fourth root of y to the fourth and the fourth root of y cubed, I can't do anything with this, right? Because there aren't enough y's for them to be cleanly fourth rooted. However, here, fourth root, fourth power, undo each other. I'm left with a y times a fourth root of y cubed. I'm going to put this one little bit of caution on this one. This is not really something we deal with very much in Algebra 1 because of the variableness in the y to the fourth. When you are in advanced mathematics, you have to do this. You have to put the absolute value around the y because this is a positive root. And so if y were negative, what comes out of this process has to be the positive version, not the negative version. And so in Algebra 1, I'm not going to necessarily check for the absolute value of y. That is an Algebra 2 and above standard. For us, I'm always going to give you the condition that any variable that I give you is going to be non-negative, so you don't have to worry about this. It's going to say in the problem statement, like, assume any variable is greater than 0 or equal to 0, and are not negative. But in Algebra 2 and beyond, you don't get that criteria. So the higher standard is to remember that if you have an even index, fourth root, square root, sixth root, and a variable comes out, you have to ensure that the variable comes out as a positive by putting some absolute values on there.